if you spawn like 20 Python processes right now to analyze some complex data models, and you forget to explicitly tell them to go home when they're finished, well, they will actually turn into zombies and eat your system's resources alive. Literally.
Yeah, it's a real and present danger for your RAM.
It really is. So today, we are going completely under the hood to help you stop micromanaging your code. We're doing a deep dive into how you can effortlessly orchestrate massive parallel computing tasks using Python's multiprocessing tools.
Right, and we're looking at this through a really unexpected lens today.
Yeah, we are.
We've got this brilliant piece of technical writing by Aaron Rose, published on the Tech Reader blog. It's called The Secret Life of Python Process Pools Explained. And Rose frames this highly technical concept inside a grand Victorian library in London.
Which is such a vibe.
It really is. Just imagine, towering mahogany bookshelves, rolling ladders, and this atmosphere where code craftsmanship is just this unspoken, absolute objective.
Okay, let's unpack this, because setting a multiprocessing tutorial in a Victorian library is, like, quite a flex.
Yeah, it's definitely a bold choice.
But Rose uses this setting perfectly to contrast the elegance of well-architected code against the brute force reality of what most of us actually write when we first discover parallel computing.
Oh, for sure. The messy reality.
Right, and we follow two characters in the piece. There's Margaret, who is a senior software engineer treating code like high-end watchmaking. And then there's Timothy, her junior colleague, who is currently just buried under a mountain of his own really inefficient scripts.
And Timothy's struggle is kind of the perfect entry point for us. He's tasked with analyzing 20 different chess matches simultaneously.
That's a lot of data.
Exactly. So he understands he needs parallel execution, right?
Yeah.
But his script is just this sprawling mess of manual commands. He's utilizing pstart and pjoin for every single individual task.
Yeah, he actually complains to Margaret that he feels like a micromanager. Like, he is manually instantiating every single worker process, telling them exactly which task to execute, and then, and this is the worst part, literally standing by the door, waiting for each specific worker to finish their shift.
It's exhausting just thinking about it.
It really is. It sounds like being a foreman on a construction site, but instead of telling your crew to, build a wall, you have to walk up to every single worker and say, pick up a brick, now take 2 steps forward, now place the brick.
Right.
It just sounds exhausting. You basically become the bottleneck of your own operation.
What's fascinating here is how the source identifies this as the trap of managing the workers rather than managing the work.
Managing the workers versus the work.
Yeah. When you first start working with concurrent execution, your instinct is usually absolute control. You assume that because the task itself is complex, the orchestration of it must be equally hands-on.
Like you have to hold his hand the whole way.
Exactly. But at a high level, your code should be focused on the logic of the task itself. If your main thread is just entirely consumed by spawning processes, tracking their process IDs, and waiting to join them well, you're paying a massive administrative overhead.
You're spending all your compute cycles on logistics instead of the actual analysis.
Precisely. You want automation, not manual labor coordination.
So Timothy is exhausted, his code is totally unreadable, and it certainly wouldn't fly in this mahogany-paneled library. Which brings us to Margaret's intervention.
Right. The whiteboard moment.
Yeah. She takes him to the whiteboard and introduces the concept of the process pool, and she frames it beautifully as a talent agency.
That's such a great analogy.
It really helps visualize it. So inside the agency, there are 4 desks, which represent the actual physical cores available on the machine's processor. And in the lobby, there's a queue of tasks waiting, which are the 20 chess matches.
And the architecture of this talent agency is entirely asynchronous from the programmer's perspective.
Meaning you just hand it off.
Exactly. You simply hand the agency a stack of work. The pool automatically dispatches a worker to an empty desk, assigns them a task, and the absolute millisecond that task is completed, that worker's handed the next item in the queue.
Here's where it gets really interesting. Because conceptually, that sounds like a perfect utopian architecture. But I have to push back playfully here. Does this actually translate to less code? Or are we just taking all that messy pstart and pjoin logic and moving the mess somewhere else, like behind some opaque configuration class?
I get that fear. I really do. But it actually fundamentally flattens the code base. And it does this primarily through the map command.
The map command, okay.
Yeah. Margaret shows Timothy how applying map to the process pool instantly halves the length of his script. The manual loops just disappear.
Oh, wow. So it really deletes the boilerplate.
Completely. You basically pass map a target function and an iterable of data. And under the hood, Python just takes over the logistics. It chunks that iterable, serializes the data via pickle, sends it across local sockets to the worker processes, and then gathers the results.
So it's decoupling the worker from the task entirely.
Exactly. You focus purely on the data set, and you let Python focus on labor. And Rose makes a really profound architectural point here regarding Python's global interpreter lock, or the GIL.
Oh, the dreaded GIL.
Right. Timothy realizes that by doing this, he isn't just breaking the GIL, he's orchestrating it.
Let's actually dive into the mechanics of that, because the classic analogy for the GIL is usually like a bouncer at a club, but that never quite made sense to me for multiprocessing.
No, it breaks down a bit.
Right. I always picture the GIL more like a single talking stick in a corporate boardroom. Even if you have 10 brilliant executives in the room representing your threads, only the person holding the stick is allowed to speak, or in our case, execute Python bytecode.
That is a much more accurate representation. Because threads share the exact same memory space, the GIL exists to prevent race conditions.
It stops everyone from talking over each other.
Right? It stops two threads from modifying the same Python object simultaneously and just totally crashing the interpreter. It makes standard Python exceptionally thread-safe, but terrible for CPU-bound parallelism.
Right, because only one person can talk at a time.
Exactly. So multiprocessing bypasses this by building 4 entirely separate boardrooms.
You spawn separate Python processes?
Yes. Each new process copies the entire Python interpreter. Each one gets its own memory space, its own variables, and crucially, its own GIL.
So you now have 4 talking sticks in 4 different rooms.
You got it. But breaking the GIL just means spawning those processes chaotically. Orchestrating it through a process pool means utilizing those local sockets to seamlessly distribute serialized data across those isolated memory spaces. And you do it without manually directing the traffic.
Okay, so the talent agency is humming along. The 4 cores are crunching the chess data, chunking through the iterable automatically. The map command has made the code beautifully concise.
It looks great.
But that brings up a systemic risk, doesn't it? What happens when the job completes? The iterable is exhausted. Who tears down the boardrooms and tells everyone to go home?
This is exactly what Timothy notices next. He sees the with statement wrapping the pool instantiation, and he asks Margaret if the agency is also a safe room.
A safe room. I love that. And Margaret confirms that the with statement acts as this ironclad boundary. It cleans up the workers and closes the desks the exact moment the work is finished.
Yes, it's a built-in cleanup crew.
It's like hiring a catering company that not only cooks a massive feast, but guarantees they'll wash every dish and lock the doors on their way out so you don't wake up the next morning to a kitchen full of zombies.
That's exactly it. And if we connect this to the bigger picture, preventing those zombie processes is a vital safety mechanism for your own computing environment.
Because a zombie isn't just a memory leak, is it? It's a very specific type of failure.
Right. A zombie process is basically an orphaned process. It's an entry in the operating system's process table that cannot be cleared.
Wait, why can't it be cleared?
Well, when a child process finishes executing, it doesn't just vanish into thin air. It sends a signal, a CHLD signal to its parent process, essentially saying, hey, I'm done, here's my exit status code.
Okay, makes sense.
But the parent process is supposed to read that status. That's what calling join actually does. And only after the parent reads the status will the OS completely remove the child from the process table.
Oh, so if your main script is poorly written, like if Timothy forgets his manual join commands, or if his script crashes before it reaches them, the child processes finish their chess analysis, but their parent never reads their exit codes.
Exactly. And the operating system is forced to keep those process IDs and a chunk of RAM hostage indefinitely. They are dead, but still taking up space on the system table. Hence, zombies.
That is terrifying.
It is. If you run a script every hour that leaves behind 5 zombies, eventually your OS just runs out of available process IDs. The system cannot spawn anything new.
And then what?
The entire server locks up and requires a hard reboot.
Which is catastrophic for a production environment.
Absolutely. So efficiency isn't just about how fast you start a task. It's about how cleanly you finish it. Leaving phantom processes draining your RAM defeats the entire purpose of writing high-quality code.
Which ties right back to Margaret's Victorian craftsmanship. A craftsman doesn't leave tools scattered across the workbench. The with statement guarantees that the parent process will read those exit statuses no matter what exceptions get thrown.
It's an architectural contract that you will not pollute the host system.
Okay, so we have the conceptual framework. We understand the memory isolation, the context managers keeping up the zombies, and the IPC happening behind the scenes. Let's evolve this into real-world application.
Let's do it.
Because the data you deal with is rarely as clean as a single list of match IDs, right? The article outlines what it calls Margaret's cheat sheet, which details how to manipulate the pool based on the shape of your data.
Yeah, the cheat sheet is super practical.
Let's stress test it. So map works perfectly if my function only takes one argument. But what if my data is messy? What if my analysis function requires the match ID, the specific player's ELO rating, and the Unix timestamp of the game? Passing that to map is going to throw a type error immediately.
It will, yeah, because pool.map expects to pass exactly one item from your iterable into your function at a time. This is where you swap to the second method on Margaret's cheat sheet, pool.starMap.
Star map, okay, how does that work?
Well, you structure your data as an iterable of tuples, where each tuple contains your multiple arguments.
So star map unpacks them for you.
Exactly. At the C-level implementation, StarMap takes that tuple, unpacks it using the asterisk operator, and injects the contents as separate positional arguments into your target function.
Oh, that's brilliant. It handles the structural complexity before the worker process even tries to execute the logic.
Right. It keeps the actual function logic clean.
Okay, so star map solves the multi-argument problem. But let's look at a different bottleneck. Say I have 20 chess matches. 3 of them are simple, 5-move checkmates. But one of them is this grueling 200-move defensive slog.
Ah, the variable execution time problem.
Right. Standard map or star map is going to block my main thread until all 20 tasks are 100% complete, aren't they? I'm going to be sitting there staring at a hanging terminal while one core struggles through that 200-move game.
You hit the nail on the head. That is a major limitation of synchronous mapping. By default, the pool gathers every single result, orders them to match your input, and then hands you back one massive list at the very end.
So if I'm processing terabytes of data,
You're wasting valuable time waiting for the slowest common denominator.
which brings us to the third tool on the cheat sheet, pool.imap.
Yes, EMAP, which stands for iterable map, changes the return type from a static list to a generator object.
Meaning what exactly for the pipeline?
Meaning, instead of blocking until the entire batch is finished, the pool yields results back to your main thread the exact moment they finish.
Wow, that drastically changes the responsiveness of the application.
It completely alters your pipeline. With IMAP, you can start writing those fast 5-move checkmate results to your database right away, or pipe them into an analytics dashboard, all while the heavy 200-move match is still chugging along in the background.
It allows for asynchronous consumption of the parallel output. That is incredibly elegant.
It really is.
But there is one final piece of Margaret's architecture that completely shifts how I think about hardware. It's this concept of automatic scaling. The article notes that if you instantiate the pool but leave the process's argument completely blank, Python handles the hardware mapping dynamically.
Yes. It queries the operating system at runtime using os.cpu count. It looks at exactly how many logical cores are available on the host machine and sizes the talent agency perfectly to match.
So what does this all mean? If I write the code once, using IMAP for a yielded generator, wrapping it in a with block for safety, and leaving the process count blank, that exact same script will automatically scale to utilize 4 cores on my local laptop.
Right.
Or seamlessly expand to utilize 96 cores if I deploy it to a massive cloud server, with no refactoring required.
Zero refactoring. It is the pinnacle of decoupled architecture. The codebase is entirely agnostic to the metal it runs on.
Okay, that feels like a superpower. Honestly, it makes me want to wrap every single script I write in a process pool. Like if I build a scraper to pull financial data from 500 different websites, I should just throw that in a process pool, right? Use all my cores to wait for those servers to respond.
And this raises an important question, but it's a trap.
Wait, really? Why?
This is a critical architectural boundary that Margaret enforces strictly.
Yeah.
Using a process pool for API requests or web scraping is a massive anti-pattern.
But it's concurrent work. I have 500 tasks to do.
It is, but it's about the nature of the bottleneck. Analyzing chess matches or crunching massive data sets are CPU-bound tasks. They require heavy mathematical lifting from your processor.
Right.
Querying a website or a REST API is an I/O-bound task, input-output. Your processor isn't doing any heavy lifting. It just fires off a network request and then sits completely idle, waiting for the external server's latency.
Oh, I see.
And if we look at the underlying cost, Spawning a full Python process is incredibly heavy. We discussed how it has to copy the entire interpreter, allocate a new isolated memory space, and set up those IPC sockets.
Yeah, the separate boardrooms.
Right. So if you use a process pool for web scraping, you are allocating massive amounts of system RAM just to create a worker that is going to spend 99% of its lifecycle blocked, waiting for a network socket to return data.
Ooh! I am renting an entire corporate boardroom, hiring a high-priced executive, handing them a talking stick, and telling them to just wait by the phone.
Exactly. It is a severe misallocation of resources. You don't hire a heavy lifting team just to stand around and wait.
That makes total sense when you put it like that.
For those high-volume, I/O-bound waiting games, the source explicitly says you should use entirely different concurrency models, like multi-threading, or better yet, Asyncio.
Because threads share memory, so their footprint is tiny.
Precisely. An event loop in Asyncio can juggle thousands of concurrent network requests within a single process, on a single core, simply by context switching whenever a task is waiting on I/O.
So a true master of this craft doesn't just know the syntax of the process pool. They know the exact shape of the hardware bottleneck they are trying to solve.
Code craftsmanship is about choosing the right architectural abstraction for the physical reality of the workload.
Process pools for heavy computation. Asyncio or threads for high latency network calls.
You got it.
Well, we've navigated some pretty complex terrain today. If you're listening, you now have the conceptual blueprint to completely overhaul your concurrent architecture. You know how to elevate yourself from a micromanaging script kiddie manually tracking PIDs into a true director of operations.
A mastery.
Exactly. You understand how map, star map, and IMAP decouple the data structure from the worker logic. You grasp the heavy cost of isolating memory spaces to bypass the GIL. And most importantly, you know how to lock the doors with statement to keep the RAM zombies out.
It really does require a fundamental shift from imperative control to declarative orchestration.
It does.
But taking that a step further, I want to leave you with a final thought to mull over. Something building directly on the implications of that automatic scaling feature we discussed earlier.
The dynamic hardware querying. Leaving the process count blank.
Yes, exactly. We noted how leaving that argument blank allows Python to abstract away the physical reality of the CPU at runtime. It just adapts instantly without any developer input.
Right.
It makes me wonder about the broader trajectory of software engineering as distributed hardware gets infinitely more complex.
In what sense?
Well, if the language can already abstract away a local 96-core processor so perfectly today, what does that mean for the future of programming? Will we eventually reach a threshold where coders have zero knowledge of the underlying metal?
Oh, wow.
We might function purely as managers of abstract intentions, simply writing the mathematical logic, while the language runtime acts as this omniscient talent agency, perfectly distributing the serialized data across massive decentralized grids that we will never even see.
That is a staggering implication. It makes you wonder if the days of needing to understand the underlying architecture of a machine are numbered. The orchestration might eventually become completely invisible.
It just might.
But until that day arrives, we still have to manage our own memory spaces. So the next time you are architecting a parallel script, take a moment to imagine yourself in that grand Victorian library. Take pride in the craftsmanship, understand the cost of the resources you're utilizing, and please ensure your context managers are locking the doors when the execution is done.
Because an elegant code base never leaves a mess in the system table.